A toast to corrosion! Hello everybody, I am Nick the Naval Architect. I remember sitting at dinner one night with some other naval architects. We're sitting around the table, talking shop, relaxing a little, and then one of the older senior engineers stood up and announces boldly, "A toast to corrosion! The best job security we can get." You see, corrosion kills most ships. Rust slowly eats away at your hull until that shiny new ship looks like a piece of brown grizzled Swiss cheese. Ugh. How do I stop this horrible thing? Well, there are no easy answers. There's no simple fix for corrosion because it isn't a simple thing. If you want to fight corrosion and preserve your ship, then we need to take some time and understand the subtle chemical process that is driving corrosion. So let's dive into the science of corrosion. Now, quick disclaimer, I'm a naval architect, not a chemist, so if this isn't 100% correctly, I ask all the chemists to be gentle. Corrosion is chemistry, but it's also electricity. At its core, corrosion involves moving electrons from one atom to another. Chemistry tends to divide this into two critical chemical reactions, where we're tracking the movement of electrons through those. First, we have oxidation, and then reduction. Oxygen atoms are just drifting around looking for electrons. They're very nefarious and like to steal them. Now, natural oxygen in the air is mostly stable and paired up. You have two oxygen atoms sitting together minding their own business. But if we add some water into the mix, then that gaseous oxygen frees up. It wants to split up with the water and form hydroxide. This process requires that we add in some extra electrons. The oxygen, it's greedy. It really wants those extra electrons, and it's going to happily steal them from any nearby atoms. So what you're seeing on your screen here in this diagram is we start off with our gaseous oxygen, add in some water and some electrons on the left, and that forms hydroxide. The hydroxide still has a negative charge on it. It's not balanced out. It's trying to find other atoms to pair up with. Remember that. We're going to come back to these hydroxide atoms later. But before we talk about those hydroxide atoms, there's an important question. Where did we get those extra electrons from? Well, along comes a helpless atom of iron. We find these in the steel hull of a ship. Quick technical note, it doesn't strictly need to be iron. There are other metals as well that also suffer from corrosion, but we're going to stick with iron for now. The thing about metals is that they will easily give up their electrons. So, the conniving oxygen atom swoops in and grabs two electrons from the iron atom. That was our oxidation reaction. We saw the first half of that when our oxygen converted into hydroxide, but what about our poor iron atom? It's missing electrons. What's it going to do? Well, here comes the second part of the process. The iron atom is trying to fill out its valence shell. It wants to replace those two missing electrons. So it runs into that hydroxide molecule, the oxygen plus hydrogen that was left over from the oxidation reaction. And wouldn't you know it, they match up perfectly to balance out their electrons. So the iron and the hydroxide get together. They form iron oxide plus some water. Iron oxide is more commonly known as rust. Hooray! The reactions are all complete, all the atoms are happy, all the electrons have balanced out, all is right with the world. The only problem is we're left with rust coming out of this. The humans have something to say. We don't like the rust. It's an inferior compound compared to the iron. Now that's the basic chemical reaction behind corrosion. But to understand the devious subtleties here, you need to understand electron travel. See, the really devious thing to understand about corrosion is these electrons. They were the main thing that was getting transferred between the atoms. But electrons travel easily through metals. See, the electrons are quite happy to skip from atom to atom and move very far away before meeting up and matching to complete the chemical reaction. Electron travel means that the site where the iron gives up the electrons and the site where the oxygen steals them may be two entirely different locations. This separation between one site and the other means that we have some very odd behavior when it comes to rust. Rust can develop very quickly. It can develop in odd locations that we didn't expect. So, how do we stop it? If we want to prevent corrosion, we either have to remove the ingredients of the chemistry, or we have to stop some part of that electron exchange. For corrosion to happen, we need three ingredients: a metal that's willing to give up electrons, oxygen that wants to take those electrons, and water to balance out the chemical process. And there's sort of a fourth requirement. You have to notice the concentration of these three ingredients. For example, if we were to take a sealed tank and remove all the oxygen, tell you that we're just filling it with pure nitrogen, the reality is we haven't actually removed every last oxygen molecule. There are still a few leftover oxygen atoms drifting around, and they can actually produce this oxidation reduction reaction. But the catch when it comes to chemistry? Nobody cares about a few atoms. That won't do much damage. To be noticeable, we need millions upon billions of atoms having these interactions. So for any significant corrosion, we need a high concentration of the ingredients. Looking at the steel hull of a ship, this is also why we see more corrosion right at the waterline of the ship. The wave action is constantly mixing in a fresh supply of oxygen. If you go deeper along the hull of the ship, deeper down away from that waterline, you're going to notice that the corrosion slows down because there's less available oxygen. So this clearly points out that removing oxygen is one strategy to completely stop corrosion. But it's not very practical. Unfortunately, our atmosphere is full of oxygen and water vapor. That's just kind of a requirement for living here on planet Earth. So we can't really eliminate the oxygen. Instead, we need to separate it from the metal. For this separation, we have delved deep into scientific principles and created a highly technical compound that is a combination of advanced chemicals. We call it paint. On commercial ships, we use paint to prevent corrosion. That's the primary purpose. If your ship happens to look good, well, that's a secondary benefit. The electrons can still make their way through the paint and through the metal. Instead, what the paint is doing is separating the water from the metal, preventing the reduction reaction. If you don't have a reduction reaction to balance out the equation, then pretty quickly the oxygen atoms are going to run out of iron that's willing to donate electrons. So if you don't have any reduction, you don't have any oxidation, and there's no corrosion. Now, I might have been a little glib when I was talking about paint. Paint is still much more fragile than the steel. And when that paint fails, we start getting pitting corrosion. What is pitting corrosion? Well, there are plenty of small mishaps that will create little cracks and little holes in that pristine coat of paint. Maybe a pebble hit the hull and chipped off a small piece, or the metal is expanding and contracting with the heat of the day. That eventually generates small cracks in the surface coating. These small chinks in the armor are just enough to allow corrosion to get in. Those small chinks are what lead to pitting corrosion, where we actually see deep pits forming along small little patches in the metal. Also critical is that these pits form much, much faster. Why, do you ask? It's because we don't have equal areas. Remember how I talked about electron transport? Well, in this case, the reduction reaction is only happening in that small crack in the paint. But those metal atoms are donating their electrons and sending them out to travel to the surrounding area. The corrosion gets driven by that contact area from all around the pit. So we have a large area that's donating the electrons, and all of those electrons are being pulled from that small little region of iron right inside the pit. It has to happen there because the pit is the only area that's actually exposed to the water so that it can exchange with the hydroxide molecules and finish the chemical process. But the electrons, they can travel to that large region all around it. And we have a lot more surface area to accept electrons compared to that small pit that's donating them. So that creates the much faster corrosion that we see in pitting corrosion. Well, we've seen how nothing is perfect. Paint doesn't last forever. Eventually it cracks, letting in corrosion. So what's the solution? More paint! The ships are constantly renewing their paint. There's touch-ups and even complete replacements. It is a constant battle against corrosion. Now, despite this effort, it's not practical to constantly renew every surface on the ship. Some corrosion is inevitable and acceptable. Yep, you heard me. The engineers expect limited corrosion. We intentionally make the metal thicker than it needs to be when we're designing the ship's hull. Everything from the plates to the stiffeners are slightly oversized. We call this extra thickness the corrosion margin. It is extra metal that you can afford to lose if you have a little bit of corrosion. The problem, though, is that corrosion is not equal and fair. It doesn't play by the rules. Instead, it will concentrate in specific locations and unevenly attack local sections of the ship's structure. And we don't have the control to add extra metal to just a few problem spots on the hull. The problem with the corrosion margin is that it's an equal blanket of protection, puts the same amount of effort in at every spot on the ship. Instead, we need more surgical precision, which leads us to sacrificial anodes. When we talk about corrosion, we're normally referring to the iron in a steel-hulled ship. Those are the atoms that we're worried about. But remember what I said, that corrosion is about transferring electrons regardless of the metal that donates those electrons. So, get a different metal. Not all metals are made equal. Some of them will give up their electrons easier than iron. Zinc and aluminum are the two preferred alternatives. So we take a lump of zinc and we bolt it onto the side of the hull in critical locations. That's our sacrificial anode. And it does exactly what it says. Instead of the iron, the zinc donates the electrons. This slowly eats away at the anode, but it helps preserve the steel. These anodes give us two major advantages. Number one, the anode is less critical. We literally bolt it to the outside of the hull. It has nothing to do with hull strength or holding a watertight boundary. And then the second reason is cost. The anode is cheaper than replacing structural steel on the hull. We can afford to just unbolt that anode and slap a new one on every 5 years. This schedule of 5-year intervals comes from an overabundance of caution. You see, we can't monitor these anodes daily. We don't know exactly how long they last. That depends on the operating conditions and the environment for the ship. This is the downside of sacrificial anodes. They're not going to completely stop corrosion, and it's a guess about when to replace them. But hey, they are cheap, which is a major benefit. Yeah, that lack of monitoring, that really sucks. What if we could monitor? What if we had some sort of gauge that could monitor the hull corrosion? Even better, what if we had a shield that completely stops corrosion along the hull surface? Well, compressed current systems offer that solution. Remember, corrosion starts because oxygen atoms are greedy. They want to steal electrons. Now, instead of taking those electrons from the poor, unsuspecting iron atoms, what if instead we just generate a supply of those fun-loving electrons? Compressed current systems do just this. They generate a mild electrical charge along the outside of the hull surface. We're pumping these free electrons along the hull surface. Now, this does require active electrical power being added in 24/7. And the electrons don't just hang out on the hull surface. To make the circuit work, electrons actually have to flow out from a source point, which we call the cathode, and they have to travel along the hull surface, going into a receiving point the anode. On top of all that, we need a sensor to monitor the electricity on the hull. You may ask, why do we need that sensor to monitor things? Well, the problem with these impressed current systems is actually the people and the nearby sea life. We could create a system that just utterly floods the hull with spare electrons, thousands of volts of power, and creating an unstoppable shield. Unfortunately, that's going to come with some side effects. When you're putting that much power into the water, that's another way of saying we're electrocuting any humans and sea life in the region. So when it comes to impressed current systems, we have to be extremely careful with the electricity supply. Let me give you an idea of just how weak these impressed current systems are. The average human can survive around 100 volts of voltage. Now, if you get zapped with 100 volts, it's going to hurt, but a few seconds of exposure probably won't do permanent damage. The impressed current systems are far, far, far below that level of 100 volts. In fact, the international rules for impressed current systems limit it to a maximum of 1.2 volts. That's only 1.2% of your danger level. Because we needed to run at this weak voltage, that means that the shield is not perfect. Corrosion can still happen, and so we're going to use impressed current systems in combination with other corrosion protection, like paint and sacrificial anodes. Well, you're thinking, gee, this doesn't sound like a perfect solution. You're right. It's not perfect, but it's definitely preferable to electrifying people. So with all of these caveats and limitations, why would we use impressed current at all? Well, cost. The impressed current slows down corrosion by a lot. So that means that your paint and your anodes are going to last much, much longer. The other benefit is monitoring. Conventional protection like paint and anodes, that's passive. You have no idea when you need to replace things. But when you have an impressed current system, you actually do get a gauge, a feedback device, monitoring. You see, the system doesn't start out at its maximum voltage. Instead, it starts lower, much lower, and then slowly increases its voltage to maintain that level of protection over time. So that gives you another way to monitor the hull. You know that if your impressed current system is pumping out at full blast, then yeah, it's time to renew the paint and replace the anodes. Your impressed current system removes a lot of the guesswork when it comes to corrosion protection. Oh, it's a lot. Corrosion can be subtle and sinister. It doesn't give up easily. The chemical processes at work, they are working on the atomic scale, finding even the tiniest crack to get through. But once we understand that chemistry, we know how to fight it. We can interrupt the links in the chemical process, stop corrosion in its tracks, because all you have to do is break one link in the train to stop the whole chemical process. So remember, corrosion requires three things: metal, oxygen, and water. Separate the ingredients or remove any one of them, and we don't get corrosion. That's the main goal behind paint and anodes and impressed current systems. Now, even with all of this technology, unfortunately, corrosion is always going to be an enemy at the gates. It is going to require constant vigilance. But thankfully, once you do spot it, the enemy is pretty easy to defeat. We've got a host of tools at our disposal. We can't ever win the war against corrosion, but with all of these tools, we can win quite a few battles. Slow it down and draw out the war. That is how we ensure a longer ship life that lasts decades. Thanks very much. I am Nick, the Naval Architect.
Thanks for watching. I hope you liked it. Say, do you wonder where all the knowledge for these videos comes from? That's actually my primary job, working as a marine consultant at DMS. At DMS, we are data-driven, digging into the regulations, looking at all the idiosyncrasies, and uncovering the reasoning behind the common sense. Check out the website, give us a call, and let's discover how we can make your ship exceptional. Thanks very much.